In this video, I'm going to talk about topics in chapter 1 of our textbook, namely measurable quantities, dimensions, units, and significant figures. Now, when we talk about a measurable quantity, there are two things that we need to know. A measurable quantity will have a numerical value and a unit associated with that. For example, if we think about the height of a person, let's say the height of a person is 175 centimeters. The numerical value 175 is one part of a measurable quantity. The other part is the unit associated with that numerical value. In this case, it's centimeters. The numerical value is based on a property that can be measured. In this case, it was the height, or more generally, the length of the person. Such properties are called dimensions. We have several base dimensions, for example, length, mass, time, temperature. They are called base dimensions. That is, they are fundamental. Now here, it shows how we represent dimensions of a measurable quantity. You have square brackets as shown here, and within the square brackets, you put the measurable quantity. That's where you put your measurable quantity. And on the left hand side, you have a symbol that represents the dimension. If it's length, then the symbol is L. If it's mass, then the symbol is M. If it's time, then the symbol for that dimension is T. And always remember the exponent. Here there's an exponent, and that is also important. So dimension of a measurable quantity includes the symbol plus the exponent. So it's not only the symbol, but always look for the exponent as well. So as I told you, these are three examples, length, mass, time, which will cover most of the measurable quantities that we discuss in our course. These are called the base dimensions, the more fundamental one. And then these are examples for some of the derived dimensions. Derived means they are results of these base dimensions. So we'll take a look at that. We'll do some examples. For example, find the dimensions of the following derived quantities. So area. So here what it means is find the dimensions. You have the square brackets. Find the dimensions of area. As you know, area is length times width. So I'm going to write, it's going to be the dimensions of length multiplied by the dimensions of width. Now length, dimensions of length is L. Dimensions of width is again L because it's a length, it's a certain distance. So multiplied by L, and then you're going to get L squared. So length squared is the dimensions of area. So that's the important thing. You always mention the symbol as well as the exponent. So length squared is the dimension of area. So similarly, dimensions of volume. So we can break volume into multiplication of length, width, and height. And then you'll have L times L times L, which is L cubed. So we can say the dimensions of volume is length cubed. Now let's look at dimensions of angle. So if you recall from my video 1, I defined angle as the arc length divided by the radius. So if this is angle theta, and let's say that this is the radius and this is the arc length S. So theta is defined as arc length divided by radius, where theta is measured in radians. So as a result, I'm going to define angle as the dimensions of angle as dimensions of arc length divided by the dimensions of radius. Now arc length has the dimensions of L. Radius is also a length measurement. So it has the dimensions of length. So then you can see this becomes 1. And this is a special type of a physical quantity where the angle has units, namely radians or degrees, but it is dimensionless. There are no dimensions. For example, we can write this as L to the power 0, where exponent is 0, and we call it a dimensionless physical quantity. Now let's look at example number 2. Find the dimensions of the following. So in the first one, we have dimensions of distance over dimensions of time. Distance is a length. So I'll put the dimensions of length L divided by dimensions of time T. L over T, this dimension is the same dimensions of the measurable quantity we call speed or velocity, which are very important quantities in physics. The second one, dimensions of distance over dimensions of time squared. So that means L over T squared. Again, this is important. This is what we call the dimensions of acceleration. In the third one, we have dimensions of mass, that is m, multiplied by dimensions of distance over dimensions of time squared. So we have dimensions of distance or length is L over T squared. And we can write it as ml over T squared. This dimensions corresponds to a measurable quantity called force, which is again extremely important idea in physics. We can use dimensions to check if an equation is correct. So if an equation is correct, we say that it is dimensionally consistent. Let's try to do an example on this. So example number 3, check if the equation is dimensionally consistent. Delta x stands for a change in position. V naught stands for initial velocity. T stands for time. 1/2 is a constant. A is the acceleration, and again you have time squared. So this is an equation that comes very frequently in kinematics when we study motion we use this equation. So let's try to figure out the dimensions of each term, and if the dimensions are equal for each term, then we say the equation is dimensionally consistent. So let's look at the dimensions of the first term, delta x, which is a change in position. As you know, a change in position is a distance, or in other words, length. So the dimensions would be L to the power 1, but I'm not going to write the exponent 1. I'll simply write L. The second term is V naught multiplied by t, that is time. V naught is a velocity. In the previous slide, we got the dimensions of velocity. So that's L over t. That's the dimensions of velocity, but we need to multiply this by time. So dimensions of time is t. You can see t and t, they cancels out in the numerator and in the denominator. So the result would be L. Now I'm going to consider the third term, 1/2 at squared, the dimensions of this entire term. Now, dimensions of a constant like 1/2 is 0. There's no dimensions for a constant. So we basically ignore that term. So we focus on the dimensions of acceleration and the dimensions of time squared. So dimensions of acceleration from the previous slide, if you recall, that's L over t squared. And then dimensions of time squared is t squared. Now you can see you have a t squared in the numerator and a t squared in the denominator. So then you have L. So all three terms will have the same dimension. So we say dimensions of delta x is equal to dimensions of v naught t is equal to dimensions of 1/2 a t squared. We don't consider dimensions of a constant, okay? So this tells us that the equation is dimensionally correct. So delta x equals v naught t plus 1/2 at squared is dimensionally consistent or correct. Dimensionally consistent. So that's how you use this analysis to show that an equation is correct. And you can check this with so many other equations that we are going to discuss in this course. Just try to see their dimensions and whether the dimensions are consistent. We already talked about what a measurement is. A measurement has two components, the numerical value and the units associated with that numerical value. We already talked about the numerical value and the corresponding dimensions. Now let's talk about the units. In our discussion throughout this course, we are going to use a standard of units called SI units. SI stands for International System. So it's called International System of Units. There are 7 base SI units. There are 7 base SI units. As you can see here, there are 7 base units. Now, for those 7 base units, base SI units, there are 7 base quantities. We discussed some of these quantities earlier. For example, length is considered a base quantity. Time is considered a base quantity. Mass is considered a base quantity. And it goes on. There are 7 base quantities, and corresponding to those base quantities, there are 7 base SI units. Here are the 7 base quantities and their SI units. For example, time is measured in seconds. Length is measured in meters. mass is measured in kilograms, thermodynamic temperature is measured in kelvins, amount of substance measured in moles, electric current is measured in amperes, and luminous intensity is measured in candela. So these 7 are called base units. The reason for that is they are fundamental. These physical quantities and their corresponding SI units are not derived from any other quantity. These forms the fundamental physical quantities that we are going to discuss in this course. Now here you can see derived measurable quantities or physical quantities and their derived units. For example, area, as you know, is distance multiplied by distance, or a length multiplied by a length. As a result, you can see the units is meters squared. Volume is width, length, height, a multiplication of all those 3 physical quantities. As a result, the unit is cubic meters. Density is mass over volume. As a result, you have kilograms per cubic meters. So these quantities are called ordinary derived measurable quantities and their SI units. Speed, distance over time, meters per seconds, that's the SI units. Moment of inertia, that is mass multiplied by distance squared, kilograms meters squared. So these are some examples for ordinary derived units which you will encounter in this course. There's another type of derived units. Those are named after scientists in honor of them. For example, force is a measurable quantity that we are going to discuss very frequently in this course, and the unit name is newtons. The SI unit is newtons and it's denoted by this symbol, uppercase N. Energy is measured in joules and this is the SI unit symbol for that. Pressure is measured in Pascal. This is the SI unit symbol. Power, watts. Then voltage is measured in volts. These are again derived quantities derived from the 7 base quantities, and these are named after certain scientists. So this is the second type of derived units. The third type of derived SI units are called special derived units. The reason for that is these units are dimensionless. We talked about dimensions earlier in this video. So these units are dimensionless units. In our course, we are only going to talk about one type of unit that is dimensionless. That's the units for angle. The unit name is radians and the unit symbol is simply rad, R-A-D. For example, if you look at this physical quantity, angular velocity, we are going to talk about that in this course. Angular velocity is defined as the angle rotated divided by the time it took for that rotation. So angle is represented by theta, time is t, and angular velocity is represented by the Greek letter called omega. So it's omega equals theta over t. So in this table, if we put the dimensions and SI units for these corresponding unit quantities, theta, there are no dimensions. It's dimensionless. As a result, we put 1. The SI unit for theta is radians. I'll put rad, R-A-D. The dimension for time is t. The SI unit for time is seconds, or s. So from the definition, omega is theta over t. So I'll put the dimensions of omega as 1 over t. The units would be radians per seconds. So you can see when you have these dimensionless units, always remember the dimension There's no dimensions. As a result, we put 1, but there's units. The units are there even though it's a dimensionless quantity. Prefixes are numbers that you put in front of SI units to make them smaller or larger than 1. For example, on the left-hand side, you can see these prefixes. So if you put the prefix, you multiply the prefix by the unit, SI unit, and then the result is less than 1. However, on the right hand side, you can see again another group of prefixes. So here, when you multiply the prefix by the SI unit, then it's greater than 1. For example, there are some prefixes that you should really know. For example, centi, milli, micro, nano, pico. The highlighted ones are important in our course. Then for larger than 1, giga, mega, kilo, those prefixes are important. For example, if you see something like this, mm, that stands for millimeters. So that means the prefix is 10 to the power minus 3 meters. Now let's try to do these examples related to prefixes. So the first one is asking us to convert 2 millijoules into joules. So there's the prefix milli here. So I'm trying to build up a connection between millijoules and joules. So I know the milli prefix stands for 10 to the power minus 3 joules. So then what I'm going to do here is that I'm going to divide the entire equation by millijoules on both sides. And then on the left hand side, I'll end up with 1 equals 10 to the power minus 3 joules divided by millijoules. Now this term, this fraction on the right hand side is called the conversion factor. It's called the conversion factor. So we need the conversion factor to make the change from millijoules to joules. Now this example is a very straightforward one, but later on I'll do some complicated ones where you'll see the importance of identifying the conversion factor and multiplying by the conversion factor in order to make the change, the transformation. So here, this is what I'm going to do. I'm going to write 2 millijoules and I want to convert into joules. So I'm going to multiply it by 1 and you can see it's not going to make any change. But now I know that 1, according to our conversion factor, can be written as 10 to the power minus 3 joules divided by millijoules, because this conversion factor is equal to 1. So now you can see in the numerator there's a millijoule unit, and then there's a millijoule unit in the denominator, and then this becomes 2 times 10 to the power minus 3 joules. So that's how you convert from millijoules to joules. In this example 4b, you have 54 gigawatts. So this G stands for giga. Gigawatts into watts. Again, I will try to bridge gigawatts to watts. So gigawatt is equal to 10 to the power 9. Giga stands for 10 to the power 9 watts. And I'm going to divide both sides by gigawatt like this. And then I end up with the conversion factor 1 equals 10 to the power 9 watts divided by gigawatt. So then 54 gigawatt times 1. It does not change anything. And in the second line, I'm going to substitute for that 1 the conversion factor, the required conversion factor for this particular conversion. That is 10 to the power 9 watt divided by gigawatt, which means 1 gigawatt is equal to 10 to the power 9 watt. So then the gigawatt terms cancels out and I get 54 times 10 to the power 9 watt. Now you can write this like 5.4, the common scientific notation, 5.4 times 10 to the power 10 watts. So a conversion factor can be defined as a ratio of 2 units that is equal to 1 or unity. You'll see that applying conversion factor, the correct conversion factor is very important because if you apply the wrong conversion factor, that could end up in a huge disaster. So you can look up this incident and it basically happened due to using an incorrect conversion factor during the refueling process of this plane. Now let's look at some examples that are more involved. So here we have to convert 1.3 miles to meters and we are given that 5,280 feet is equal to 1 mile and then 3.28 feet is 1 meter. So we have to use this information in order to make the conversion. So I'll use these two information to come up with the conversion factors. So I know that 1 mile is equal to 5,280 feet. So then I'm going to divide both sides by 1 mile and then I get my first conversion factor. So that is this one. Then from the second information, I'll get my second conversion factor. So that is there's 3.28 feet in 1 meter. So I'll divide both sides by 3.28 feet and then I'll get that conversion factor. Over 3.28 feet. So now you can see I have these conversion factors. So this is one conversion factor and then this is the other conversion factor. So now I need to convert 1.3 miles. And simply what I'm going to do is that I'm going to multiply this by 1. So 1.3 miles times the first conversion factor. That is, I'm converting the miles into feet. That's what I'm doing in this conversion factor. One mile. And then in the second conversion factor, which is again just 1, I'm converting the feet into meters. Over 3.28 feet. Now you can see the miles over here in the numerator cancels with the miles over here in the denominator. The feet in the numerator cancels with the feet in the denominator, and the only unit that I end up is meters. So this answer, if you simplify this, you would get 2100 meters. So this is the correct way of writing meters. So I'll use that, and also you can express this in terms of scientific notation like this. 2.1 times 10 to the power 3 meters, and that's the answer. That's the amount of meters in 1.3 miles. So the important thing is that here we can consider the units as algebraical terms. So we can simplify units similar to what we do with algebraic terms. So this is something important to note down. In this example, we have to convert 36 kilometers per hour into meters per second. So 36 kilometers per 1 hour. So the first conversion factor would be related to distance or a length. I know that there's 1000 meters in 1 kilometer. So this is my first conversion factor, and that's related to a length. The second conversion factor is going to relate to a time. I know that 1 hour comprises of 60 minutes. And then the third conversion factor is again related to time. That is a conversion between minutes and seconds. I also know that 1 minute comprises of 60 seconds. So now we can cancel out the units just like algebraic terms. There's a kilometer here that cancels out with that kilometer. Then I have 1 hour and that cancels with this hour. And then minutes with minutes. And then I end up with meters over seconds. So I have 36 multiplied by 1000 divided by 3600 meters per second. So this you can see is simply 10 meters per second. So that's how you convert kilometers per hours into meters per seconds. Let's look at example number 7. It says Proxima Centauri, which is a star, is 4.25 light years away from our sun. How much is it in kilometers? So you need to understand that light year is a measurement of distance. Or length. It's not a measurement of time. Even though it says year, it's not a measurement of time. Then the definition of light year is the distance traveled by light in one complete year. So that means, according to the definition, 1 light year is equal to the speed of light multiplied by an year. So you can see on the left hand side you have a distance. The first term on the right hand side is a speed. The second term is time. So distance equals speed multiplied by time. Now since they are asking the answer in kilometers, I will have to convert the speed of light in terms of kilometers. Usually speed of light is written as 3 times 10 to the power 8 meters over seconds. However, this is in meters. I need to convert this into kilometers. So I know that 1 kilometer is equal to 1000 meters. So this is my first conversion factor where I converted meters into kilometers. Now 1 year. I need to convert this 1 year into seconds so that it will cancel out with the seconds over here. So I know that 1 year is equal to 365 days. So 1 year, and then our conversion factor, 365 days is equal to 1 year. This is our second conversion factor. This is a conversion factor. This is a conversion factor, but this is not a conversion factor. It's just 1 year by definition of how we define light year. And then I need to convert days into hours. I know that there are 25 hours in one day. And then I'm going to convert hours into seconds. I'm going to convert it directly without going through minutes. I know that 1 hour is equal to 3600 seconds. You can do it like this, or if you like, you can go from hours to minutes and then from minutes to seconds. But I thought that this is much more easier. So now I have these unit terms, and then I can cancel them out just like algebraic terms. So I can see a meter in the numerator and a meter in the denominator, year in the numerator, year in the denominator, days, they cancel out, hours, that cancels out, and even the seconds over here cancels out with the seconds over here in the denominator. So the final unit I end up is kilometers. So I have 3 multiplied by 10 to the power 8 multiplied by 365 multiplied by 24 multiplied by 3600 divided by 1000. And the only remaining unit is kilometers, which is exactly what we need. We need the answer in kilometers. So if you simplify this, you can put this in scientific notation, and then you should get 4.02 times 10 to the power 13 kilometers. So 4.25 light years is equal to 4.02 times 10 to the power 13 kilometers. Let's look at example number 8. Convert 60 degrees to radians. We know that 360 degrees is equal to 2 pi radians. So if I divide both sides by 360 degrees, I get 1 equals 2 pi radians divided by 360 degrees. So this is going to be our conversion factor. However, you can see the numerator and the denominator can be further simplified. As a result, I get pi radians over 180 degrees. So that's going to be my final conversion factor. So now I need to convert 60 degrees into radians. So I'm going to multiply 60 degrees by the conversion factor, pi radian divided by 180 degrees. So 60 degrees cancels with 180 degrees, giving me a 3 in the denominator. As a result, 60 degrees is equal to pi over 3 radians. So that's how you convert 60 degrees into its radian value. Now let's look at significant figures. Remember that significant figures are meaningful digits, that are digits that we can measure with certainty. There are basically 4 rules that you need to know when working with significant figures. The first rule is trailing zeros of a whole number are not significant. So here you have an example 65,000. The trailing zeros are not significant. Only the digits 6 and 5 are significant. As a result, this number has 2 suffixes. So if you see something like this, another example, let's say 1000. Here there's only one sig fig because the trailing zeros are not significant. The second rule is leading zeros in a decimal number are not significant. So now you need to look at a decimal number. If there is leading zeros, that is zeros before a digit, then those zeros are not significant. Here you have 0.005. There's only one significant digit, that is 5. Okay. For example, if you have 0.01, then again you have one sig fig, which is the digit 1. So we say 1 sig fig. As an example, if you think about this number, 0.02545, here the leading zeros are not significant, but you have these digits 2545. Those are significant. So here there are 4 sig figs for this number. The third rule is zeros between non-zero numbers are significant. So if you have non-zero numbers and zeros between those non-zero numbers, then they are significant. So again, you can see as a result, you have 4 significant figures. If you have something like this, let's say 3.001, then there are 4 significant figures in this case. 4 sig figs. Rule number 4, trailing zeros of a decimal number are significant. So you can see that's the decimal point, so it's a decimal number. If you have trailing zeros, these 2 zeros are significant. So then you add these digits, these are significant, so there are 3 significant digits here, and the trailing zeros are also significant, so you have 5 sig figs. In this case, you have 0.50, the leading zero is not significant, but this trailing zero is significant. So as a result, you have 2 sig figs for this number. Another important thing to understand is that significant figures are not decimal places. For example, if you think about this number, this is a decimal number. Now there are 6 decimal places. So remember, there are 6 decimal places for this number. But there are only 3 sig figs for this number. In terms of sig figs, there are 3 sig figs. Because I have applied rule number 2, the leading zeros of a decimal number are not significant. As a result, only digits 5, 6, 4 are significant. But when you consider decimal places, you also include the zeros after the decimal point. So keep that in mind. That's a very important thing to distinguish the difference between significant figures and decimal places. Now let's look at adding or subtracting numbers and the significant figures of the result. For example, we determine the significant figures looking at the decimal places. You look at the smallest number of decimal places, and that's going to equal the decimal places of the final result. For example, let's sum up these 3 numbers. When you sum them up, your result would be 2.275 meters. Now, if you look at the decimal places of the original numbers that you add up, for the first term, you have only 1 decimal place. For the second term, you have only 2 decimal places. For the third term, you have 3 decimal places. So then you look at the smallest number of decimal places, which is just 1, and that should equal the decimal places of the final result. So we only consider up to this point. However, we need to round it off because this is 0.275. So when we round it up, we get 2.3 meters as the answer. Similarly, if we have two numbers to subtract, we look at the number with the smallest decimal places. For example, here we have 4 decimal places, and this number we have 6 decimal places. So the result of this subtraction will have 4 decimal places. So the result is 0.032479, and these are the 4 decimal places that we are interested in. So there's a 4, after that there's a 7, so we can round this 4 up to 5. As a result, the final answer would be 0.0325, and we based this subtraction looking at the decimal places of these two numbers. When multiplying or dividing factors, that is numbers, instead of looking at decimal places, we look at significant figures. We look at the significant figures of the least accurate factor, and that's going to be the significant figures of the final result. For example, if we look at the multiplication of these two factors, we have 2.43 meters per second multiplied by 34.32 seconds. So here the answer would be 83.3976 meters. However, we only consider the significant figures of the least accurate factor. So here we have 3 sig figs. In this number or factor, we have 4 significant figures. So we only look at 3 sig figs for the final result. So that means up to here. However, we are going to round it up because after 3 there's a 9. So the final answer would be 83.4 meters. So that is how we come up with the final answer looking at the significant figures of the least accurate factor. Similarly, if we have two factors to divide, again we look at which factor has the least significant figures. So here we have 5 sig figs. However, on this number we have 3 significant figures. So when we divide this, we are going to get 532.98701. So we only look at 3 sig figs, so that is up to this number. However, after the decimal place we see a 9, so we can round it up, and after rounding up it's going to be 533. That's how you do this example. With this, I conclude this second video, and I will talk about vectors in my third video. Again, a very important topic for you to succeed in this course.